Go for it.
Objectives. Or you want me to read that too?
Oh yeah, what is that?
Section 1, Theory of Heat, Unit 1, Heat, Temperature, and Pressure.
Okay.
Objectives. After studying this unit, the student should be able to define temperature, make conversations between Fahrenheit and Celsius scales, describe monocular motion at absolute zero, define the British terminal unit.
Good.
Objectives continue. Describe heat flow between substances of different temperatures. Explain the transfer of heat by conduction, convection, and radiation. Discuss sensible heat, latent heat, and specific heat. State atmospheric pressure at sea levels and explain why it varies at different elevations. Objectives continue. Describe 2 types of barometers. Explain PSIG and PSIA as they apply to the pressure measurements. Okay, so heat, temperature, and pressure.
Hey, you want to read this whole, you want to read the whole thing?
Oh yeah, y'all want to help?
Is that what he's saying? He's saying for all of us? I don't know.
Huh?
He's saying for just you?
No, this is everyone.
Oh, I don't know. It's just for, I don't know how you do it.
So instead of he does everything, like we all have to volunteer some way, And so, like, you know, I could read through like a couple of them, and then like when I stop, you guys know. Unless you guys want me to read it out, I don't care.
This is how we usually do it notes.
Just read it all, or
and then he'll stop us when he needs to stop us and explain some things.
Okay, what's the second?
Okay. Heat, temperature, and pressure. Heat energy moves from one substance to another as well as between the molecules of a single substance. When we need to be more specific than hot or cold, we refer to temperature. System pressures are obtained by using a refrigeration gauge manifold.
the level of heat, or this is temperatures. The level of heat or heat intensity measured with thermometers. English system, Fahrenheit. Metric system, Celsius. Fahrenheit, absolute scale. Rankine. How you say that one? Rankine?
Huh?
Rankine?
Rankine.
Celsius, absolute scale, Kelvin. Absolute zero, temperature at which all molecule movement stops, negative 46 Fahrenheit. 460 Fahrenheit.
Yeah. Okay, so negative 460 is absolute zero. So in the Rankine scale, just like right here, for the Rankine scale, it's 0 at minus 460. So that's an absolute scale, and the same thing on the Celsius scale with Kelvin.
0 Kelvin.
That's their absolute temperature. So at minus 460 degrees, everything stops. Everything. So all molecular movement stops. We have not obtained that. We don't know what that looks like because we can't get down that low. Even in space. Space is minus 458.
Really?
Yeah.
It's not absolute zero.
Not absolute zero, because there's still some heat in there. So that means that even at there's 2 degrees, that still means there's molecular movement happening. So the molecular movement is happening everywhere in all matter. So in this table right here, there's molecular movement. It's way down in the molecules are moving around. And those molecules move around according to the amount of heat in this table. So the hotter this table, the faster those molecules are moving around. So that's just it. What heat is basically a movement of molecules. So the more movement, the more heat's there. Okay, so make sure I get this, okay? Yeah. So we're gonna be converting temperatures. So, and I say this because you may be working on a lab refrigerator or freezer that's, the readout is in Celsius. So we're used to Fahrenheit, so we're gonna have to convert that stuff in the field, right? Because they're gonna, the lab is gonna say, you know, it's gonna say -30 Celsius, you know, because some labs, some medications, stuff like that have to be kept at a certain temperature. It's gonna be Celsius, but what's really going on is what we're used to is Fahrenheit, so we're gonna have to figure out what those are, what those numbers mean, and what temperature we're actually at. Okay, so in the example is converting Celsius to Fahrenheit. Let's do this. We're gonna go Celsius. We say Celsius. How about this? We're gonna do 29 degrees Fahrenheit, Celsius. No. Degrees Celsius. Get with it. Pay attention. Okay, 29 degrees. What is that in Fahrenheit? Oh, it's right there. It's right there.
We gotta figure it out.
We'll figure it out.
Okay.
What?
Okay.
Fahrenheit is equal to
So it'll be 84.
what?
Yeah, well,
In parentheses goes first.
1.8 times Celsius plus 32 degrees.
So that'll be 84.2.
It's what? 84.2?
Yeah.
Okay, so Fahrenheit. Okay, so this means that next time you're in France and it says it's going to be 29 degrees outside, don't take a coat. Okay?
Yeah.
Because it could be 84 degrees.
Yeah.
Okay. So, and we can go the other way too. So why don't we do that? How about that? Let me give you a, let's do something we're familiar with. How about 98.6? Why does that sound familiar?
That's today.
That's what we need to be.
Huh?
Is that today?
That's our body temperature?
Oh, okay. What is it in Celsius? What? Yeah.
Celsius? I think it's like
Fahrenheit. Fahrenheit. Fahrenheit.
Minus
37 degrees, so it's 37 Celsius.
Wow, you got it. It's not an apple, is it?
Huh?
Is that an apple?
definitely an apple.
Yeah.
I'm just calculating.
I know, is that an apple?
Yeah. Apple.
Okay, 37 degrees Celsius. Right?
So take a cup.
Huh?
Oh no, don't take a cup.
Okay, so we got the idea how that works?
Yeah.
Okay, we're gonna have a project where we're gonna do that. We're gonna do this up. It's gonna be a lab.
Understood.
What?
Pretty sure I know that. So would the Fahrenheit ever be a like a negative? Make the make it out come to a negative? So like in the parentheses, will it, the solution, the answer to that problem in the parentheses will it be a negative?
Yeah, it can be negative. Yeah.
Could be. It's gonna trip you out.
Okay.
You'll see.
All right. So we're gonna talk about heat now, right? What does that say? I can't read.
Heat is the motion of molecules. Heat cannot be created or destroyed. Heat can be measured and accounted for. Heat can be transferred from one substance to another. Heat travels from a warmer substance to a cooler substance.
Okay, there's a lot of stuff there, right? Heat is a motion of molecules. Molecules.
Molecules.
I mentioned that already, right?
Yes.
Heat cannot be created or destroyed. Heat is always.
Absolutely.
Whoa. Heat can be measured and accounted for. heat can be transferred from one form or one substance to another. So we can convert heat energy from, we can make heat energy, we can make other kinds of energy. We use sunlight to make heat, and we can use, we can convert that energy to electrical energy, stuff like that. So it can be converted, and it can be transferred. Heat always goes from where?
Hot to cold.
Always. Always.
Always.
It doesn't go from the bottom to the top.
Hot to cold.
It doesn't go, Magic Bob is a pilot, right?
Mm-hmm.
Okay. So his hot air goes where?
To the cold. To the atmosphere.
Goes up. Hot air goes up. Heat travels from hot to cold. Ooh.
Introduction to heat continued. Quantity of heat in substances is measured in British terminal units. BTUs.
Okay, what's a BTU?
The British terminal unit.
That's what it stands for. What is the definition of a BTU?
The quantity of heat.
There's the definition down there. What does that say?
I was gonna get to it.
Okay.
Figure 1.6. Oh, 1-6. 1 British terminal unit BTU of heat energy is required to raise the temperature of 1 pound of water from 68 degrees Fahrenheit to 69 degrees Fahrenheit.
Okay. Or 1 pound of water, 1 degree.
So it's 1 degree.
1 degree, yeah. That's what a BTU is.
1 degree.
That's the science behind it. This all started back in Britain, right? With all British units, right? Obviously, British thermal unit started in Britain. And in Britain, everything is measured by pounds. It's like water, pound of water. We measured in what? Quarts and pints and gallons, right?
It's weird.
They always measure stuff in pounds, so it's why it's kind of a little bit confusing. So this is not a pint of water, it is a pound. Okay? So 1 BTU is equal to is the required heat to raise 1 pound of water 1 degree. That's the definition of a BTU. Okay, we're going to use the term BTU a lot. Okay?
Conduction. Heat energy travels from one molecule to another molecule with a substance within a substance. Heat energy travels from one substance to another. Heat does not conduct at the same rate in all materials.
Okay. So the type of heat transfer, there's 3 types of heat transfer that we're going to talk about. Conduction is one of them. As you can see, if that's a copper rod, it says copper right there. And you're putting it in a flame, what do you think is going to happen to that other end of that copper rod? It's going to get hot. And it's not going to take very long either. It's going to go fast because copper is a very good conductor of heat and a good conductor of electricity. So molecules will move really fast and really quick, and that's the conduction, what they're talking about. Molecule to molecule is what they're calling conduction. You're just feeling it. You're feeling the effects. Okay, so we'll move on to the next type of heat transfer.
Convection. Heat transfer through a fluid from one substance to another. Natural convection utilizes natural fluid flows such as rising of warm air and falling of cooler air. Forced convection uses fan or pumps to move fluids from one point to another.
Okay, so convection, a little bit different. So an example of convection would be this guy right here. This baseboard heater. It's a little electric heater on the bottom of the baseboard of the structure. As the hot air rises, we know that hot air rises because you guys came out ProDam, right? It rises up here, and the cool air, which is heavier, it falls to the ground, it falls to the bottom, and it actually pushes and it helps that cool air go into the baseboard heater and heat up again. It's just like a natural type of convection. So it's using the air, the warm air, to heat the room. Okay? like a convection oven. How's a convection oven work?
As a fan back? No.
It heats up the air, which cooks the food.
Wow.
So all ovens are convection, right? Except for microwaves. Oh,
Radiation. Radiant heat passes through air, heating the first solid object with which the heat comes in contact. These heated objects in turn heat the surrounding area. Radiant heat can travel through a vacuum.
oh, wait, what?
Radiant
Can
heat.
travel through a vacuum.
Like
What?
a sun ray. Radiation continued. Radiant heat can travel through space without heating it. Example of radiation, an electrical heater that glows red.
Okay, what's another example of radiant heat?
The sunlight.
The sun. It's obviously not heating up to space at almost minus 460 degrees Fahrenheit. That ain't getting hot. But the Earth is getting hot, right? So that's radiation. Another example would be a microwave oven is radiant heat. So here's an example, and this I use this because it's a good analogy. It's a good a demonstration of the three different types of heat transfer. Y'all been camping before? Okay. Build a campfire? Okay. This heat here that you feel from that campfire, sitting in front of it, that's radiant heat. The heat that you feel when you put your hands on top, that's convection, because it's heating the air and you're feeling the hot air, right? And of course the conduction is the rod that's actually in the fire that's making the heat transfer. So those three, all on the same heat source, three different types of heat transfer.
Makes sense.
Okay. I know you know that slide. Okay, we're going to talk about this now. What is that? What? Okay. Good job.
Sensible heat. Heat transfers the results in a change in temperatures of a substance. Sensible heat transfers can be measured with a thermometer. Examples of a sensible heat transfer: charging the temperature of a sample of water from 68 Fahrenheit to 69 Fahrenheit. That's the Bluetooth.
The what?
What is it? BTU.
What is it?
Heat test? I don't know, I just recognize the 1 degree difference, so.
BTU.
Yeah,
BTU.
that's what we talked about that. That was a BTU, that's the 1 degree. The sensible heat is, what's the temperature in here? Do you know?
70 degrees.
No.
60.
72, come on, it's always 72 in
I
here.
don't know that.
That's a sensible heat temperature, or that's a sensible temperature in this room is 72 degrees. Okay? It's actually 73, because I said 73. So that's the one we can measure with a thermometer. This is where it gets exciting.
Latent heat. Latent heat transfer results in a change of state of substance with no change in temperature. Also referred to as hidden heat. Latent heat transfers cannot be measured with a thermometer. Example of latent heat transfer: changing 1 pound of ice at 32 degrees Fahrenheit to 1 pound of water at 32 degrees Fahrenheit.
Whoa, wait a minute.
It's the same.
Wait a minute.
Latent heat continue. Three terms that are important to understanding refer to latent heat transfers: latent heat of vaporization, latent heat of condensation, latent heat of fusion.
Okay, so heat that can't be measured with a thermometer. If we can't measure it with a thermometer, then how do we know it's there?
Because we can see the effects.
Yeah, but what is that effect that you see? What do you see?
Sensibility.
Melting?
Huh?
Is melting be one?
No. Would you say melting? Yeah. When ice melts, the ice and the water are both the same temperature. Okay, as it makes the change, It's 32 degrees, you know that, because last month we calibrated our thermometers in ice water to check the, so as ice is melting, it's changing state from a solid to a liquid. As it's changing that state, it stays at the constant temperature of 32 degrees. The same way with boiling water. Is that weird?
That's kind of weird,
Yeah.
I always thought it was, I mean, it's obviously melting, so I just thought it's increase of heat.
It would be like the radiation of the heat that makes it melt?
No, so it's latent heat. That's the heat that's causing it to change state. So just like boiling water boils at what temperature?
212?
212. Okay, can you overheat that water?
Yes.
Can you heat it past 212?
No.
No, it just stays at 212. From that point, any more heat, it turns to vapor. So it changes state. So the heat that's making it change state is latent heat. So that's causing it to make liquid to steam or liquid to vapor. So the three terms they're talking about is latent heat of vaporization. What would that mean?
Vaporization, like cold ice. There's a CO2 ice. Yeah.
No.
No?
That's the latent heat of causing water to boil. If we're talking about water.
Oh yeah, vaporizing.
What about latent heat of condensation?
When it's steam turning into water.
Yeah. It's condensing back into liquid. This is the one I always like. Fusion. It always sounds bad. Latent heat of fusion. What do you think they're pertaining to that?
Water to ice.
There you go. Water to ice.
Yeah.
Being fused together.
Yep.
Making it solid. Okay, do you know what the term is where it goes from solid to vapor and skips the liquid state?
No. It's
No?
something else. Can't remember.
Called sublimation.
Sublimation. Yeah.
You should know that.
I should know, I should have.
It was on a crossword puzzle.
Forgot about
Made you look though.
it.
Okay, so knowing this, knowing that the liquid, we're going to be dealing with condensation and vaporization in refrigerant. Okay, we're not going to deal with fusion because refrigerant doesn't fuse.
No, it doesn't.
It goes back and forth from liquid to vapor, and that's what causes the refrigeration effect. Okay, this is all science now. Okay, this is your chart, and this chart is 1 pound of water. You can see where it starts here at 0 degrees. This is Fahrenheit, and this is BTUs going that way. So we're starting off at 0. So we're raising the ice temperature from 0 to 32. Okay, once it reaches 32, we're adding the latent heat. Notice that it stays at 32 the entire time it reaches this point, which is 32 degree water. See that? 32 degree ice. Focus, okay. 1, and then we go to 2, which is 32 degree ice, and then 0.3 is 32 degree water. So it's staying constant at 32 degrees as it's changing. So we're going from 32 degree water to 212 degree water. So how many degrees is that?
Yeah.
180, right? 180 degrees. So in order to raise 180 degrees, to water, we need 180 BTUs of sensible heat. No latent heat is involved in changing the temperature.
Because there is no light.
Well, because the latent heat is involved in making it into steam from this point here. So 212 degree water, more heat that it absorbs, it becomes steam. And that's how much heat is going to require. Now, latent heat is not measured with a thermometer, but it is measured in BTUs. So that's how we know where it is and what's happening. Okay? So I think it's time for a break.
I'll take it. I'll take it.
That's all.
We'll take break.